Welcome to our team's presentation on our term project of natural language processing with sentiment analysis. Our team members are Darian Hotchick, Kyle Nope, Matthew Warren, and Strider Coleman.
Natural language processing is a growing field due to the immense computer usage. The demand to analyze large quantities of text has never been greater, leading to the development of techniques like sentiment analysis. Our goal is to analyze text with sentiment analysis, a process that entails breaking text into smaller syntactic structures and evaluating their polarity. We will derive polarity by creating a recurrent neural network. The neural network will input a sentence and return the polarity. With any machine learning problem, additional models should be created for comparison. Therefore, we've built naive Bayes models and decision trees to go alongside our recurrent neural network. With each unit, we'll derive a polarity indicating the positivity of each sentence. There are three classes: positive, negative, and neutral. Each class is represented with an integer: 0 for negative, 1 for neutral, and 2 for positive. The neural network will place each sentence into one of these classes.
Now that we have discussed what sentiment analysis actually is and gone over the target or goal that our team set for our project, we will now discuss the process we went through to achieve that target or goal. The first part of our process was to actually find a data set to use. To do this, we used a very popular website called Kaggle. It is a website that offers many different types of data sets for machine learning and data science. We chose to use the data set, the State of the Union corpus, which gives all of the State of the Unions given between 1790 to 2018 in text file formats. We imported all of these text file formats to our Python code. And one of the reasons we chose to use this data set is right now a lot of sentiment analysis is used for areas such as reviews of different products and movies and restaurants, etc. So we were trying to see if using a political data set, we can create a model that has alternative uses to just a review-based system. Once we had the data set imported, we had to transform it into a usable format.
After the dataset has been imported, the next step was to go about transforming the data. Essentially, the process involved cleaning the data of the necessary elements in order to reach our established target. Firstly, we read the State of the Union text data into an object called a data frame. Next, we split the data into sentences within the data frame while simultaneously removing all punctuation and stop words. For the third step, we assigned polarity to each sentence and added these polarities to the data frame. The polarities assigned were integer values that act as scores for each sentence. Following the transformation of our data, we had to go about pre-processing transform data so that it may be inserted into a neural network. The first step involved tokenizing each sentence that had been individualized within the overall data frame. The tokenization process involves each sentence being assigned a specific token. Next, the data had to be split into training and testing sets for the later purpose of implementing our model. Using a dictionary, each created token had to be mapped to integer indices. This collection of integer indices would then form multiple integer lists. Essentially, one integer list would correspond to a set of indices that map to a token which refers to a sentence. At this point, The data still needs to be modified further before it can serve as proper input into a neural network. The key point here is that integer lists are of different lengths due to sentences being different lengths in the original text. This causes an issue with input in a neural network, but a process called vectorization allows for a solution. Thus, we had to vectorize each integer list through a process called multi-hot encoding. This process converts the integer lists into vector sequences of ones and zeros, but of equal length. Following step 4, we then store these equal-length vector sequences into tensors, which are objects found in the machine learning platform TensorFlow. Lastly, the vectorization process had to be completed for both the training and testing sets that were established earlier in step 2.
The neural network is built with a stack of 3 dense layers. Each layer contains an activation function. The first 2 layers consist of rectified linear unit activation functions of 64 units each, followed by the softmax function of unit 1. The 3 layers will then output the sentiment. The neural network uses root mean squared propagation as the optimizer, a descendant of gradient descent, using a decaying average of partial gradients in the adaptation of the step size for each parameter. For loss, categorical cross-entropy is used, computing the loss between predictions and labels. The model will be inputted with the vectorized sequential sentences and will output each corresponding sentiment. Hello everyone, welcome to our sentiment analysis demonstration. We will be discussing our process demonstrating the sequential recurrent neural network we built, trained by the State of Union speeches. We will be using the smallest unit possible, a sentence and a label. The label represents the polarity of that sentence. In this case, the label is 1, because that sentence is neutral. Next, we'll transform our sentences into a sequence of integers, with each integer representing a word. The use of sequential integers allows the recurrent neural network to use a different size of n-grams per step. Following the sequentialization, the sentences need to be vectorized, and the labels need to be converted into an array. After the transformations, the sentences will be passed into the model, outputting a label. And lastly, we'll evaluate our model. As you can see, the model predicted 1, which is the correct answer. And since we only had one case, evaluated our accuracy at 100%.
We got results on 2 of our sequential recurrent neural networks, one that was trained over 20 epochs and one that was trained over 4 epochs. The one that was trained over 20 epochs had a training accuracy of 86.6%, with a validation accuracy of 86.5%, where the sequential recurrent neural network trained over 4 epochs had a training accuracy of 86.6% and a validation accuracy of 86.1%. We ran some other classifying models to compare our results to see if our model that we had trained was superior or inferior to some of the other classifying models. So other models that we ran for classifying was naive Bayes, Bernoulli naive Bayes, K-neighbor, and decision tree. The training accuracy was inferior for all 4 of those, with the highest being naive Bayes at 85.6%. However, the validation accuracy, we did get some comparable results with naive Bayes and Bernoulli both scoring about 88 and 87%, and also the decision tree also scoring 87% for the validation accuracy. However, the K-neighbor scored below 80% for the validation accuracy, making our model superior in that sense. The contributions made follow the established target of an NLP model implementation, which produces a multi-class classification on an imported dataset for the purpose of sentiment analysis. We are testing the idea of building additional sequential neural networks to improve natural language processing on additional resources rather than just reviews. Our work relies heavily on Francois Chalet's work in deep learning of Python, which focuses on the same target, but he implements it using a binary classification.
As the team leader, I wanted to take a second to speak about the individual team contributions made toward this project. We broke up the process of reaching our target into a few phases. Initially, during the planning phase, each team member worked closely to plan out our approach towards our overall goal. Issues that we ran into initially with the implementation allowed the team to rethink our approach collectively and follow other resources such as the work provided in the earlier reference textbook, which allowed the team to adapt the references to meet our requirements. Throughout the implementation phase, each team member played a pivotal role towards understanding the core topics of what was being attempted and had a hand in adding essential lines of code. Specifically, certain aspects were worked on, such as the removal of punctuation and stop words by myself, Darian Hodzik, further transformation through vectorization and model creation by Kyle Knope and Strider Coleman, and finally the addition of various classifying models as well as results comparison by Matt Warren.